So did everyone get my email? I assume. Yes? Okay. We're putting our old server, actually a new version of the old server online, so it'll be easier for me to deal with the website in the future. But I will email you as necessary. All right? Okay, so we're talking about entanglement, in particular this entanglement in the context of what we call bipartite systems, two parts. And those parts are often called, we have the joint system and the subsystems, okay? The parts are the subsystems. They are what the analog are degrees of freedom in classical dynamics. When we think about multiple degrees of freedom, each degree of freedom is like a subsystem, okay? And there's some joint Hilbert space for the joint system, which we're taking to be a tensor product space. It's important that it has this tensor product structure to be able to talk about entanglement. Right. So if we have these bipartite system, the two systems can be correlated with one another. And we say that the systems are classically correlated if the joint system has this form. As I say, the state of the joint system has this form. I can think about it as a statistical mixture of two different states, one for system A and one for system B, and if well, actually it doesn't matter what I say about this distribution. If it's correlated, classically correlated, then the joint probability distribution, they're statistically dependent. I can't write it as if the probability distribution factorized, we would say that A and B were statistically independent from one another. Here, if this is not true, we would say that they're correlated. Okay, so that's a classically correlated system. Whether it's this or not, in quantum mechanics, and this is just a jargon, we say that the system is separable. Even though it's not a product, necessarily a product state, we call it separable in the sense that it can be written in terms of this convex combination of product states. Okay, it's a jargon, and that's just how it is. If the state cannot be written in this form, then we say that the quantum state is entangled. Okay, so entanglement is not this. Okay, now determining whether or not a state in general can be written in this form is a really hard problem. Okay, in the general context. And it's a whole, I mean, you know, that was a big enterprise in the late 1990s, people trying to think about the whole questions about, and into the early 2000s, about the problem of general questions of entanglement. But if we restrict our attention to the case where the joint system is pure, okay, so that's just a particular case. That's the case we're typically most interested in. Then it turns out that it's easy to know whether or not the system is entangled or not. We'll show that, we'll remind ourselves in a minute, and see how much entanglement there is. And for the case, for this specific case, if the joint system is pure, then this is a one-to-one statement. If it's separable, then it's a product state. And if it's a product state, then it's separable. Okay? Obviously, if it's this, then it is in this form, with this just being one term, the product of those two. Okay? And if it's not a product state, then it's entangled. Okay? So if I cannot write the joint pure state as a tensor product of two states, one state for subsystem A and the other for subsystem B, then I say it's entangled. Okay? But for mixed states, it's a complicated story. If the joint state of the system is mixed, then there's not an easy relationship. Separability doesn't mean product state, it means this. Okay? All right, that's just a little extra info. Now, the other thing that we talked about last time is that the notion, how we calculate the marginal state. This is the quantum mechanical equivalent of the marginal probability distribution. So if I have the joint probability distribution, I know how to marginalize and get the distributions for each individual random variable. This is the quantum mechanical generalization of that, where rho is the density operator. Okay, so if I have the joint density operator for the two systems together, then if I want to know what is the state of the system for subsystem A, which tells me something about the probability of measurement outcomes that I would make if I were to do measurements of A alone, irrespective of what's going on with B, then the way I would find that quantum state is I would trace out subsystem B. That's the jargon we use. And that's the partial trace. Okay? And importantly, as we discussed, as we have discussed, if we have an entangled state for the joint pure, if the joint system is pure and entangled, then the marginals are mixed. So the subsystems are not, can't be described. There's missing information in describing the state of the subsystems. And that missing information is in the correlations, which we don't have access to. And that's another hallmark of entanglement, an important one. We talked about these different contexts, correlations, and mixedness. Okay? Very good. All right, so let's continue where we were, what we were talking about. So we were talking about never mind, I give up. We were talking about the Schmidt decomposition. So the Schmidt decomposition is the whole story when talking about bipartite entanglement for pure states, which is what we care about most. Okay? So what we said is that if I have a bipartite system, and if that, I can always write that bipartite system as a decomposition in the standard basis. So I take as a standard basis a product basis where these are basis vectors of subsystem A, and these are basis vectors of subsystem, this is B, and this is A, right? And in principle, these can both be infinity, but for the moment, we'll just talk about them as finite dimensional. Okay. So these coefficients are the probability amplitudes for the expansion in that basis. So this I'm calling I comma j. Right? That's the product basis. All right? So these coefficients form the elements of a d by d rectangular matrix. And any such matrix can be written in terms of what's called the singular value decomposition, the SVD. That's a linear algebra result. And we can write the matrix gamma as some unitary matrix that's a dA by dB matrix. I mean, it's a square matrix, dA by dA. A matrix that has only elements on the diagonal, but it itself is rectangular, and another unitary matrix. And for convention purposes, in the Schmidt decomposition, we take that to be the transpose of the standard matrix. So these are unitary. And this is diagonal. And so written as a matrix, what this is, I'll just sort of sketch it. We have let's say that dA is smaller than dB. What the heck? So this is a dA by dA matrix. And then I have, this is U transpose. Then I have some rectangular matrix like that. And then I have a square matrix like that. So this is dA by dB, and this is dB by dB matrix. Okay? And this matrix only has non-zero elements on the diagonal, where the row equals the column. Okay? So now I'm going to have all kinds of blocks here. Let me try to write that with more clearly here. So this is my matrix here. This is dA by dA. This is dB minus dA by dB minus dA. Okay, so let me explain what's going on here. Here's my square unitary matrix, U, and it's the transpose of the U that I care about, and this is my square matrix V, okay? And I've written in terms of blocks here, okay? Now, in particular, this guy, the maximum possible number of so this guy has zeros everywhere other than on the diagonal. It's a diagonal, okay? These coefficients, U mu, lambda sub mu, mu goes from 1 up to mu max, are known as the singular values. Okay? Those singular values are in fact all positive real numbers or non-negative real numbers. Okay? Now, the biggest possible value of U max is what? dA in this case, right? So this can be at most the minimum of dA and dB. In this case, I've taken dA to be smaller than dB. So whatever the smallest dimension is, that's the maximum number of non-zero singular values I could possibly have. But I might have fewer than them. In this case, I have fewer, all right? U max is two less than I have 2, 0 in this particular example that I've drawn here, okay? In this case, mu max is dA minus 2, okay? All right, and how do I find those singular values? Well, in principle, those singular values are such that if I look at the matrix, this matrix or this matrix, they have the same non-zero eigenvalues. And since those are positive matrices, right? Because look at that, this dagger is a positive matrix. Its eigenvalues are positive. And those eigenvalues we call lambda sub mu squared. Those are the eigenvalues of these matrices. These matrices have the same eigenvalues. This is a dA by dA matrix. This is a dB by dB matrix. But they're both Hermitian positive matrices. I can diagonalize them. They will have the same non-zero eigenvalues. Obviously, if dA is smaller than dB, this thing is going to have at least zeros in this block, right? But it could have even more zeros depending on this maximum value of this, right? And then there is a basis transformation, which are the eigenvectors of these two matrices, okay? So the eigenvectors of these two matrices are what we call, in this case, V mu and U mu. Those are the eigenvectors of these matrices. This is on A and this is on B, because this is a dA by dA matrix, this is a dB by dB matrix, okay? So by doing the singular value decomposition, the way I do it is I diagonalize these two matrices. You can find their eigenvalues and eigenvectors. Now, actually, we rarely do this in practice. You see, it's a kind of formal thing. Sometimes we might throw it on Mathematica and make it do it, but that's mostly, you'll see as this lecture progresses what this is really about, as opposed to an algebraic thing of doing a Schmidt decomposition. Okay, so importantly then, what we have is the following. We have a basis transformation which says that for mu equals 1 up to whatever the maximum mu is, where we have the maximum number of non-zero singular values. Okay, those singular values are very important. Then the basis vector u mu on subsystem A is given by the elements, the superposition of the original basis So this vector is a vector in the Hilbert space for subsystem A, and it is just a superposition of the original basis. And V mu on subsystem B is this superposition. So this is a vector in the Hilbert space of subsystem B, and it is a superposition of these. And since this is a unit vector, this are the elements of a unitary matrix, right? Because it preserves the norm. And vice versa. That's what the U and V are. Their basis change. Okay? So, with all of that said, we have the following. That says then that the state of the joint system can now be written when I plug in the singular value decomposition that Uij is equal to U mu I lambda mu V mu J sum over mu. That's the singular value decomposition. These are the unitary matrices, and I took the transpose, and that's the diagonal elements. Let me just finish this and I'll answer the question. Then this comes together in the final result. All right, Brian, yes, you had a question.
Sorry.
No, please.
In the first two there, you're summing over U or I and J?
Oh, good question. That is absolutely the case. Thank you for paying attention. Absolutely. I'm summing over I, and I'm summing over J. Thank you. But I only have to sum up to that. Typically, I would sum over the whole dimension, but I only sum up to that amount. Okay, those are the only parts that contribute. All right, let's take a look at this expression because it's really the whole story here. So what we have in the, by performing the Schmidt decomposition, whereas in this original expression we had a sum over two indices here, and wasn't obvious a priori whether or not this state can be written as a product state or not. You can't just look at it generally and see that. Here you can. Okay, so what this is saying is that because these states is over one index, and these, as we'll see in a moment, will prove an essential point here, that if mu max is 1, then we have a product state. That is to say, for the pure state, it is separable. If mu max is greater than 1, then it is entangled. Okay? And by the way, this is called the Schmidt rank. So the Schmidt rank is the number of non-zero singular values in the singular value decomposition of this matrix that I called gamma. Okay? So if the Schmidt rank is 1, it's a product state, right? That's obvious. That's a product state. If the Schmidt rank is greater than 1, then I say for sure there exists nothing I can do to turn it into a product state. And then we call the system entangled. How can we see for sure that this system is entangled when mu max is greater than 1? Well, one way to do that is to look at the marginals. We know that if we had a pure state and we marginalize, we look at the so-called reduced density operators, which I like to call the marginal density operators. If those marginals are mixed, then the joint was entangled. Okay, so let's look at that. Let's look at the density operator here. Does everyone see what I did? I took the outer product of the state with itself. Had two dummy indices here. One mu and the other mu prime. Okay? Okay, so now I want to know what is the marginal state for subsystem A. What I do is I trace out B. Well, what happens when I do that? Well, I do the old trick, right? So I trace over B over here, and that becomes this. Well, what is that? That's a delta function. How do we know that those are orthogonal? Well, we know that because if this was an orthonormal basis, I should have said that this guy was, these were orthonormal. I chose them to be so. Then a unitary transformation preserves the inner product. So this, if these were orthogonal, so are these. Okay. And similarly, these are orthogonal. So these things are called the Schmidt vectors, by the way. And they are orthonormal. So, given that fact, what is this equal? Our marginal. Well, delta delta prime, so this is equal to sum over mu. I'll call it P mu. U, mu, A, U, mu, where P mu is, I'm just calling the square of that. Those are the original eigenvalues. Right? And what is this equal? Well, I trace out the marginal for subsystem A. For subsystem B, I trace out A, right? And what is this going to be equal to? This. Exactly. So this is a very important result. And let's analyze it. So, what we see here is that if the Schmidt number, the Schmidt rank, also called the Schmidt number, is greater than 1, then what could you say about these? Are these mixed states or pure states?
Mixed.
They're mixed, right? Only when it's equal to 1 is it pure. And since the marginals are mixed and the overall state was pure, the overall state is necessarily entangled. Moreover, we see interestingly that the spectrum of these guys is the same. In other words, these are the eigenvalues, so the p-mu's, which were just the square of the Schmidt numbers. Okay, yeah, I've gotten the language confused. These are not, this is the Schmidt rank, not the Schmidt number. The Schmidt numbers are the lambdas themselves. They're the Schmidt coefficients. So this guy are the eigenvalues, or the non-zero eigenvalues, they both have the same diagonal representation as a matrix. Of course, if the dimension of one of these subsystems is bigger than the other, then there will be additional zero eigenvalues for, say, B versus A. If B was a bigger matrix and you diagonalized it, you would find a whole bunch of zero eigenvalues. But the non-zero ones are the same for both of them. That's interesting. In this bipartite system, the subsystems look the same. They look equally mixed. They have, and the these guys are the eigenvectors of the marginals. Up to a phase. So here's one way you might think about getting at the Schmidt decomposition. That seems easier than doing a singular value decomposition. You write the joint state out, you trace out one of the subsystems, and then you diagonalize the marginal. When you do that, you can find the eigenvalues and eigenvectors of row A and row B, right? Then the Schmidt coefficients are just the square roots of those probabilities, and you got the eigenvectors. Now, that seems like cheating, because I seem like I have everything about the joint system by looking at just the subsystems alone. How could I possibly reconstruct the joint state of the system by just looking at the subsystems alone? Where did I cheat? Here's where I cheated. Because the phase matters. The actual state depends not just on the magnitudes of these things squared, but it depends on the relative phase. And that phase is buried here in what these transformations are, which you really need to get from this singular value decomposition. the relative phase in the superposition matters. And you can't get that by looking at the pieces alone. That's a property of the whole. Okay. Nonetheless, you can get a whole lot up to those phases by just looking at these marginals in this way. All right? Very good. Okay, so with that, let's come back to this board. So now we can try to quantify. So, you know, there's this kind of digital question. Are you an entangled state or are you not? Well, we can answer that question by just asking, is the marginal a pure state or is it a mixed state? And that's we can get by tracing out and looking at the number of non-zero eigenvalues of the marginals, right? That's equivalent to what the Schmidt rank is of the joint state, okay? But I might want to ask, how entangled are you, right? There's a continuum. We know, of course, that the dimension, okay, so the Schmidt rank can be between these guys, right? That's what we can have, right? So we can ask, one way of measuring entanglement is to ask how many non-zero Schmidt coefficients are there? Which is to say, what is the Schmidt rank? So measuring how much entanglement, or I should just say quantify, measure is a loaded word. Quantifying entanglement. So a coarse way is just to ask, what is the Schmidt rank? So it's between 1 and this, or this being separable, no entanglement. And more non-zero elements means more entanglement. But how much more? And if you look at this, if I were to look at let's say I had the following, let's say I ordered them in such a way that 99.9% of it was in mu equals 1. And then mu equals 2, 3, 4, ... up to dA had, like, you know, a tiny itsy bitsy teeny weeny amount of non-zero. So it added up to 1, but it was all concentrated at this one guy. Doesn't seem so different, even though this guy would be full rank, we would say. It would have all, it had all non-zero eigenvalues. And in fact, a physical state that you have some information is always going to have that, because it's a real number, for God's sakes. Nothing is going to be 0 to, or 1 to infinite precision in our knowledge of it, right? We always have some finite precision information. So this seems like a pretty darn coarse and stupid measure from anything practical. view. So what should we do to quantify this? Well, we want to know, in some sense, how spread out these eigenvalues are. If we had a situation where we had 1 over dA equal spread of all equal probability of all the Schmidt vectors, we would say that was pretty mixed, and thus the joint state was pretty damn entangled. Okay, maximally so, in fact, if that were true. So the way we often do it is we look at the missing information in marginals lead to mixedness. And so that the way we measure information is through entropy. Entropy is a way of quantifying how much more information I need to specify the full thing that I don't have. And so that entropy is of the probability distribution is that. Now, this entropy is also what we call the von Neumann entropy. So this is the entropy of the probability distribution. The one that I sketched as a histogram over here. It tells me something about how much information is missing to specify which outcome is there. And if I wanted to be very contemporary, I might measure this in base 2 so that I can measure the missing entropy in bits. How many bits of information? Often we do that. We don't have to. We can measure it in natural log. It's the number of nits we need. That's kind of gross. Yeah?
So last semester we had some like quantification of like how mixed a state is,
exactly.
Like the trace.
Yeah, exactly. So you're right on target, Matt. Let's connect those. Absolutely. So this is the entropy of the state, which is, or entropy of the probability distribution, which is equivalent to so the two states have the same non-zero eigenvalues, and thus they have the same entropy of the state. This is what we call the von Neumann entropy. Okay. So that's the way we typically measure. We typically call this the if we have a bipartite pure state, then the entropy of the marginals is what we call the entanglement. That's how we define it. We measure entanglement this way. It's the amount of missing information in the marginal. They're one and the same. And what's the maximum entanglement I can get if I have a, so that we'll call it E. What is it between? How is it bounded? What's the, so I can have zero entanglement, right? That's the case where one of the probabilities is 1 and the rest are 0. And what's the maximum it could be?
Log of mu max.
Log of mu max. where this can be as big as dA or dB, depending on the minimum. So if I have two qubits, two-level systems, what's the maximum amount of entanglement I can have? 1 E-bit is what we call it, 1 entanglement bit of entanglement. Okay. What if I had a qubit coupled to a Q-trit, a 3-level system? It's the same thing. I can never have more than 1 E-bit because dB, it would be bigger. I can only have, it's only the minimum. What if I had a 2-level system coupled to an infinite dimensional system? Also, can never have more than 1 bit of entanglement here. Okay? And that's how we typically measure. And this is an unambiguous thing to do when I have a bipartite pure state. Now, as Matt was suggesting, if you weren't thinking about, oh, I want to do this in terms of information, I just wanted some coarse way of measuring how mixed is the marginal state. How would you do it? Exactly. So that's another measure, right? I can look at trace, say, rho A squared is the mixedness of the marginal. And of course, that's just the sum of the square of its eigenvalues. Okay? This is sometimes known as the linear entropy, because it's what you get if you take the entropy function and you do this small expansion where everything is close to 1 plus epsilon will give you this. This is sometimes known as the linear entropy. But it's an equally good measure. It just doesn't measure it in bits in the same way. But it is what we call an entanglement monotone, meaning it's a monotonic function. The more entangled, the more mixed. Cool. Excellent, excellent. Let's see, what am I forgetting in this lecture to tell you? Oh yeah, that's where I'm going. Glad I have my notes with me. All right. So that's basically the whole story about measuring entanglement of bipartite pure systems. You need the Schmidt decomposition, or equivalently, you know something about the marginals. And up to the overall phase, the marginals tell you about how mixed things are, and therefore how entangled everything was to begin with. All right, so I want to say a few words about generating entanglement, sort of in a generic sense, and then we're going to talk about the quantum optical sense. All right. So, this is about generating quantum correlations. All right, so let's say that I have two subsystems. Right, so I have my Hilbert space. This is my Hilbert space. And let's say at time t equals 0, the two systems, let's say we have an overall pure state, initial time, let's say that we had a product state. There were no correlations. The question is, if this thing evolves as a function of time according to some Hamiltonian, what is the requirement on the Hamiltonian that the state at a later time is entangled? Okay, so let's say this is at time t equals 0. The state at a later time is that, let's just say for a time independent overall Hamiltonian. Okay. So now this is the Hamiltonian. So if the Hamiltonian is such that we have non-interacting degrees of freedom, well, that would mean that there's no, the Hamiltonian acts locally, so to speak, on subsystem A and subsystem B, right? So there would be some Hamiltonian that does something to A but does nothing to B. And okay, the Hamiltonian can be written as a sum of Hamiltonia that act separately on A and B with a sum. Then we say that the Hamiltonian is separable in A and B. Right? And if that's true, then my joint time evolution operator in that case for this case, the unitary evolution on the joint system and because these guys commute, right? Because anything on A, these two operators commute, then I can write this as a tensor product of two operators, right? One for Hamiltonian A, and I'm going to, I should never have written an H bar. I won't write it again. At least not today. Okay? So, in this case, we would say that the unitary map is separable. Now, I want you to be careful here. This involves a product, and that involves a sum. The Hamiltonian is the generator of the map, and when the generator is a sum of two terms, then the evolution operator factorizes into a product, okay? And if this is true, then the state, and I started in a uncorrelated state, a separable state, then the state at a later time I just separately evolve this has gotten to the point where I'm gonna open a new pen. Right? So that is a fancy math for saying something intuitive. That if the systems don't interact, if the subsystems don't interact with one another, and they started uncorrelated, then over time they just evolve, the state evolves in a separable way, and there are no correlations that are generated between the two subsystems, and it remains separable or unentangled. Okay? So, what does it take to create entanglement? It requires a unitary map that can't be written as a tensor product of a unitary map that acts on each subsystem independently. It cannot factorize in that way, which means the Hamiltonian must have an interaction term which correlates, right? So, if on the other hand, so if the Hamiltonian for the joint system cannot be written as in this form, then so if it might have some kind of interaction, sometimes when we just write the A and B, we don't have to write the tensor product 1 on B and 1 on A, because it's obvious what we're talking about. So if that's the case, then the unitary operator will not be of this form, cannot be factorized, and in that case, this guy is not equal to a product state. So the moral of the story is entanglement is generated by non-separable interaction. All right. But now things get, there's some subtlety here. So, let's go back to an example we all learned when you take your first semi-advanced quantum mechanics. Let's look at the hydrogen atom. Okay. So, if I look at the hydrogen atom, I have, typically I would think about there's an electron and a proton, right? I have the kinetic energy of the electron, I have the kinetic energy of the proton, and then I have the Coulomb interaction, ignoring all the relativistic and spin effects. Okay? So, is this Hamiltonian separable or not? Well, it's not, right? I mean, there's an interaction term here. So this is not equal to a Hamiltonian that acts only on the electron and does nothing to the proton, and a Hamiltonian that acts only on the proton doing nothing to the electron. That's not true. So this is not separable. Or is it? Because you know that you always do the hydrogen atom by kind of separating coordinates of sorts, right? So I can also write this Hamiltonian, if I like, as a kinetic energy of the center of mass plus the relative momentum, that is the relative motion of the relative energy with the reduced mass, right? And then minus the potential energy associated with the relative distance, right? And this Hamiltonian, so I'm sorry, this is a not equal, but this is an equal. And so I can separate this in terms of relative coordinate and center of mass, but I cannot separate it in terms of electron and proton. And this brings me to an important and often understated point, which is that entangled versus separable depends on which degrees of freedom we're looking at. Said another way, what tensor product decomposition? So if I write the Hilbert space in terms of one degree of freedom is the electron and the other degree of freedom is the proton, I'll see certain things differently than if I took my decomposition to be the center of mass motion of the electron and proton together and the relative motion of the electron proton. In fact, if I come back to this point, an important point here is that, let's see, where did that go? So, let me say this here. If I have a Hamiltonian that is of this form, which is, I can be written as the sum of the two, then the eigenfunctions, or eigenvectors, are product states. Right? Because I can just find the eigenvectors of this and find the eigenvectors of that, and then the product is also an eigenvector of the sum, with the eigenvalues just being the sum of the eigenvalues. On the other hand, if the Hamiltonian did not separate, then the eigenvectors would not be products. they would be entangled states. And that brings me to the point that I'm making here. So as you know, remember, we do this separation of variables. It's kind of a PDE trick that you know from methods, so that you can find the overall eigenvectors as just, you look at the product states, right? So in this case, the eigenvectors of the Hamiltonian for the hydrogen atom are products of the eigenfunction of the relative motion and eigenfunctions of the center of mass. In this case, the center of mass is a free particle, unless I put the atom in a trap or something like that. And then these are the usual Lagrange polynomials times spherical harmonics, right? On the other hand, those states are the product states. The eigenfunctions would be, the eigenfunction of the center of mass and the eigenfunction for the relative motion. That is an eigenfunction of the overall thing. But on the other hand, these things are not separable in terms of the electron and proton. The electron, if I were to look at the electron and proton, they're entangled with one another. So whether or not a system is entangled or not depends on what degrees of freedom I'm considering. Okay. So another this is the messy coordinates. Jesus, one behind here. Okay, because that one's too big. So another point I want to emphasize is the business of entanglement and change of basis. So let's say that I have, we wrote the state is a, let's say I have a pure state, as we have, and as we wrote, let us write this as a decomposition in some product basis. Okay? Now let's suppose that I change the basis in Hilbert space. So let's just say that I have some new basis vectors. Let me call them G and H. Okay, so this is just another basis. This is a set of basis vectors for, say, 2 qubits. These might have been spin up and spin down along Z, and this might be spin up and spin down along X, right? There'll be a different matrix here. So gamma ij is the probability amplitude like this, and delta is the probability amplitude like that. They're 2 different superpositions. It's just a change of basis. But what I've done is I've changed the basis locally. Okay? So I went from a product basis to a product basis. Okay? So I had some change of basis, which what we would say is a local change of basis. The term local is a little bit loaded here because I'm not having a notion of these things being spatially anything. It's just that I have 2 degrees of freedom, and on 1 degree of freedom I can, I change the basis on this guy and I change the basis on that guy. Okay? So now I ask you the following question. Do these have the same entanglement? Sure, the entanglement has nothing to do with that choice of basis. Okay? So I can change the basis on these guys, and this is the same, there's the same amount of entanglement, no matter what. In fact, if I have a new state, this is a more active, this was sort of a passive change of basis. If I have a new state like this, which I obtain by acting separately. So this is a different state. But I obtained it by applying this unitary operator to this. How much more entanglement does this state have than this? They're the same. How do you see that? Well, I can just think about it as I've applied a local rotation to this guy, and I wouldn't change this matrix at all. And the amount of entanglement was just related to something about the Schmidt decomposition. And said another way, this kind of unitary involves local evolution. It doesn't involve creating different correlations. So whatever correlations existed before don't change if I evolve locally. I needed the interactions. But the other point is, if I just looked at whatever basis, the change of basis of A and B don't in any ways affect how much entanglement there is, right? On the other hand, so the moral here is that a local change of basis does not affect entanglement. On the other hand, let's just, for example, say I have two particles on a line. As we said, we might say they have position and momentum. Now, I could take the joint Hilbert space to be the Hilbert space associated with the motion of particle A and particle B. Alternatively, I could look at the center of mass and relative coordinates. They're the same Hilbert space, but two different decompositions into degrees of freedom. I might say the thing I really care about is, let's make this guy a heavier particle. The center of mass position and center of mass momentum, and the relative position and relative momentum. That's a perfectly good description. But as we just saw, depending on the tensor product decomposition that we do, that does change the entanglement. If I had something which was a product state of center of mass and relative motion, that will be entangled between 1 and 2. So you might think about this as a change of basis. It's not really, right? It's a change of the whole structure of Hilbert space itself. How we chopped it up into pieces. And how we chop it up into pieces matters in a very subtle way, as you'll see, I guess, next time when we talk about this in lecture, how this kind of change of tensor product decomposition can have a very subtle effect on the notion of entanglement. Okay? Yeah?
So if we measure in the center of mass relative distance basis, we'll get like the center of mass position and the relative distance, so we can figure out where both of them are, but we can't figure out where each of them is.
That's right. So if we had a state prepared in this way, we could be in an eigenvector of the, say, center of mass position and an eigenvector of the relative mass. We could do that. And they could be, for example, I could have something which is something that approaches a position eigenstate of the center of mass and a momentum eigenstate of the relative momentum. I could do that. That would be a state that if I measured it, I would know something about the center of mass, but I couldn't know both. Yeah. This is actually, as we will talk about, this was the Gedanken experiment that Einstein and Podolsky and Rosen contemplated, as we will discuss. Okay. So I could also, if I liked, I could have put it in the eigenstate of the relative. That's another possible state. But I won't know where either particle is simultaneously. I will have this information. As we will see, the particular one that EPR looked at was a how do I want to say? What did I want to say about this? I think I want to leave that discussion for a little bit later. But I guess all I want to say here is that this state is entangled. The position and momentum of particle A and particle B are entangled, even though the center of mass and relative coordinate are separated, right? So I can prepare a state like this, where this outcome is completely uncorrelated from that, but the position of particle A is correlated with the position of particle B, and the momentum of particle A is correlated with the momentum of particle B. And it was this kind of state that Einstein, Podolsky, and Rosen thought about in their thought experiment to kind of see how local realism challenged the Heisenberg uncertainty principle. We'll discuss that more when we get there. Very good. All right.